In this lesson we're going to look at the chemical erosion of limestone and the formation of stalactites, and we're going to do so in the context of reversible reactions and applying the principle of Chatelier, as we have been doing in the last few lessons, to understand the processes that are involved. First of all, let's start with this, that you know that limestone is principally a rock made from calcium carbonate, and that calcium carbonate or limestone is chemically eroded by carbonic acid, and carbonic acid is formed when carbon dioxide dissolves in water. Okay, so we've got water here dissolving carbon dioxide gas, forming carbonic acid, okay, and that carbonic acid reacts with the limestone. Now, it's a very weak acid, and the reaction will take place slowly, very slowly, but it is a reversible reaction, and the product of that reaction are calcium ions and bicarbonate ions. Okay, so bicarbonate is the carbonate ion with a hydrogen attached, so that has a negative charge, and you would call this really calcium bicarbonate. Okay, but the calcium bicarbonate is soluble, it dissolves in water, so we're just representing the ions in aqueous solution here. Okay, so the first thing to know is that it is a reversible reaction. As we've been learning in the previous lessons, that a reversible reaction can go in either direction. It can go in the forward direction, or it can go in the backward direction, or the reverse direction. Okay, now the direction in which the reaction goes depends upon the conditions that are involved. Things like the temperature, or the pressure, or the concentration of the various components in either in the reactants or in the products. Okay, and that's what we're going to be looking at today. What affects the direction in which this reaction goes? Okay, so let's just remind ourselves of Le Chatelier's principle. We say that once any chemical reaction is in dynamic equilibrium, that's to say, once this reaction has reached dynamic equilibrium, what that means is that the amount of the product and the amounts of the reactants stops changing, they become fixed. Okay, and what Le Chatelier's principle states is that once dynamic equilibrium has been reached, then any change that is applied to the conditions around that reaction, any change, for example, a change in temperature, or a change in pressure, or a change in concentration, then the reaction will favour the direction that opposes that change. Okay, and in the particular case of the reaction that we're looking at today, we're particularly interested in the effect of the change in concentration. Going back here, that's to say what we're going to be looking at, and the item of interest in this reaction is the concentration of carbon dioxide. Okay, so we want to think about what happens to this reversible reaction when the concentration of carbon dioxide is changed. Now, Le Chatelier's principle states that, repeating again, if once the reaction is in dynamic equilibrium, if you then increase the concentration of one of the substances in that reaction, then the reaction will favour the direction that reduces that concentration. So if the concentration of carbon dioxide increases, then in order to reduce the concentration of carbon dioxide, the forward reaction will be favoured, so that the position of equilibrium is shifted towards the dissolved calcium and bicarbonate ions. So you're going to end up getting a greater amount of calcium and bicarbonate ions in order to reduce the concentration of carbon dioxide. The reaction will move in the forward direction. Conversely, if the concentration of carbon dioxide for some reason falls off or drops down, then the backward or the reverse reaction would be favoured, okay, in order to increase the concentration or level of carbon dioxide present in the reactants. So the concentration of carbon dioxide can affect what's happening in limestone scenery. Okay, to help us understand this, let's have a look at this diagram. And while we're considering this diagram, we're going to bear in mind this equation all the time. Okay, so what we've got here is we've got a layer of limestone rock, and you're probably aware that limestone rock tends to have all these sort of like fissures and cracks in it. That's the way it is, and let's draw some of these fissures in. There we go. And on top of the rock, you see we've got a layer of soil, all right, and on top of the soil we've got some plants growing and trees and all sorts of vegetation there. And what's going to happen is that these plants are going to die, their leaves are going to fall off, and they're going to fall onto the soil, and they're going to start rotting, and there's all sorts of microbes in the soil which is going to help to decompose that rotting vegetation. And as a result of all these microbes, these tiny animals in there which are they're all breathing out carbon dioxide. So in the soil we're going to get quite a high concentration of carbon dioxide gas due to the presence of all of these tiny organisms, due to the decomposition of dead or rotting material present in the soil, a high concentration of carbon dioxide. So what happens then is it rains. So the rain's providing our water here in the equation. The carbon dioxide is provided by this rotting vegetation, this decomposing organic material. And what's happening here is because of this process that's going on in the soil, we've got a high concentration of carbon dioxide up here in this part of the limestone rock. So what's going to happen is then the rain falls onto the soil, it dissolves the carbon dioxide. Okay, so you've got water with a high concentration of carbon dioxide seeping through the fissures in the limestone rock, and because we've got a higher concentration of carbon dioxide, then this forward reaction is being favoured. So that means that the calcium carbonate is going to dissolve to form the calcium ions and the bicarbonate ions. Okay, so what's taking place here then is effectively chemical erosion of limestone rock, the calcium carbonate being dissolved, this forward reaction being favoured. And so gradually, these fissures are going to start opening up over time. I mean, by time we mean over hundreds of thousands, millions of years. They're going to start getting, bigger, and you're going to get all sorts of interesting formations, forming, in the limestone rock as a result of that. So initially it starts off as chemical erosion, taking place, the actual calcium carbonate getting dissolved by the carbonic acid, by the carbon dioxide that's dissolved in water. And what's going to happen is all of these little trickles of water seeping through these cracks and fissures. The cracks and fissures are going to open up, the channels of water are going to get larger and larger every time it rains, and you're going to get physical erosion taking place eventually, and these fissures are going to get widened and opened up, and eventually, somewhere down here millions of years later, as a result of both chemical and physical erosion, you're going to get some sort of cave system forming. We're not really going into that in too much detail here, but you get some sort of cave system forming here. Now what happens in the cave is different to what's happening at the surface where the rock is near the soil, where the concentration of carbon dioxide is much higher and the forward reaction is favoured. But when it reaches the cave, you'll note that in caves plants can't grow, there's no vegetation because there's no light. No photosynthesis can take place. So you get no plants, no vegetation, no living organisms can really survive living inside a cave. So as a result of that, there's going to be a reduction in the level of carbon dioxide. Whereas in the soil, you've got all these living organisms breathing out carbon dioxide, and carbon dioxide being produced by the decomposition of dead organic material. Well, there's no living organisms, no dead organic material to decompose, so the level of carbon dioxide is much lower. So we've got a low concentration of CO2 here. As a result of that, the reverse reaction is now favoured in this equation. and so the position of equilibrium is shifted towards the left-hand side of the equation in order to increase the level of carbon dioxide present in the environment of the cave. As a consequence of that, calcium carbonate is reformed, and it reforms as stalactites and stalagmites. Okay, you remember, so this iron-rich water, that's to say, this water here, which is rich in calcium and bicarbonate ions, comes down into the cave, and then the reverse reaction takes place, and the calcium and bicarbonate ions react to form CO2, water, and calcium carbonate. And so calcium carbonate starts getting deposited on the roof of the cave, gradually over, again, hundreds of thousands of years, forming these stalactites. Okay, so the water comes in, drips down, the reverse reaction takes place, calcium carbonate is formed as the stalactite. Some of this reverse reaction will take place in this stalactite, but some of the water still remains. It drops down, drip onto the floor where the same process occurs. Okay, the reverse reaction still continues, and the ions continue to rejoin to form the water, carbon dioxide gas, and calcium carbonate on the cave floor, and so we get the reverse process. Here we get a stalagmite. Okay, so the stalagmites form on the floor. Stalactites, remember, stalactite, because they have to hold on tight. All right, that's how you remember that one. They have to hold on tight to the roof of the cave. Okay, these are forming because this all-important reversible reaction is being driven in the reverse direction inside the cave, where the concentration of carbon dioxide is very low, repeating again, whereas at the surface, on the surface of the limestone rocks, near the surface of the limestone rocks, where the concentration of carbon dioxide is much higher due to the activity of organic material at the surface, then the forward reaction is favoured, and that's where the chemical erosion takes place. So the forward reaction is the chemical erosion. Reverse reaction is the stalactite formation.